Okay. Yeah. So I'm going to finish 4.4. The last little bit I want to do, I'm going to go over Fermat's little theorem briefly, just a statement and a little illustration, one possible illustration. We'll see more later. Um, and then one little topic which is of interest but not directly related to RSA. It's related to other kinds of sorry. This, yes, there we go. This, um, but I'll get to that in just a sec. Sorry, in the chat. There you go. Excellent. We're all good. Okay. So first thing, so Fermat's little theorem that we saw last time. Let me restate it and illustrate it a little bit. This will be used in RSA. This is fundamental. So here is the statement. So P is a prime, and A is an integer not divisible by P. Okay. There we go. Then Fermat's little theorem says that if you consider A to the power P minus 1, this will be congruent to 1 mod P. Magic. Okay. I gave you a proof of this. This is not an obvious fact. Okay, I'm just stating, so if you remember last time I stated part 1, part 2, the second part, you just multiply this, this congruence by A on both sides, and it's valid even if A is divisible by P, but it's trivial. But that's really where, that's really the important part of Fermat's little theorem. Okay, so if you take any integer not divisible by P, you raise it to the power P minus 1, then the number you will get is congruent to 1 mod P. And again, this is not an obvious thing. Let me just illustrate one little baby use of this. So an example of its use, but it's just a sort of, I mean, it goes obviously way beyond this. So we're asked to compute, I think it is, yeah. So I'm asked to compute, find 7 to the power 222 mod 11. Okay, again, I repeat, if you have underline mod or bold font, then it means this is a number. So you want the function, right? So you want to evaluate this. And this is like, there's a bunch of exercises of this form. Yeah, the web works, it should be up. That's what I wanted to say. I've had a little glitches here and there, but the web work should be up very soon. Okay. And there's some problems of this form, of like this one in the web works. So 7 to the power 222, well, if you have a big enough machine, you can compute it, obviously, but this is not the point. You can actually do this pretty easily by hand. I'm going to show you, okay? The fact that we're looking at mod 11, 11 is a prime, okay? So 11 is prime, right? And obviously, 11 does not divide 7. Okay, so it means that we have the setup of Fermat's little theorem. Okay, so in Fermat's little theorem, P is 11 and A is 7. Okay, so what does this theorem say? It says that if I raise 7 to the power 10, P minus 1, I will get 1 mod 11. Okay, this is what the theorem says. Can I use this to compute 7 to the power 222 mod 11? Yes. Here's how it goes. Actually, I think once you've seen it like this, you would probably be able to actually finish this, right? But let's just do it. So notice that 222. So basically I want to get 10 involved in here. So what is this? That's 22 times 10 plus 2, right? So 222 is 22 times 10 plus 2. So 7 to the power 222 is 7 to the power 22 times 10 plus 2. Okay, so far so good. Okay, so now let's just rewrite this. So this is 7 to the 22 times 10 times 7 squared, right? If I'm adding exponents, means I'm multiplying. And by the same token, 7 to the power 22 times 10, this is the same as 7 to the power 10 to the power 22. Yeah, just elementary arithmetic. Okay, so 7 to the power 222 is 7 power 10 to the power 22 times 7 squared. So if now I consider this mod 11, right? So 7 to the 222 is equal to 7 power 10 to the power 22 times 7 squared. If I consider this mod 11, then 7 to the power 10 is 1, right? So this is the same as this mod 11. And of course, 1 is very convenient because you can multiply as many as you wish and it won't give you a big number, just a small number. So this is, so it means that 7 to the power 222 is congruent to 49 mod 11. And 49 is obviously congruent to 5 mod 11. So 7 to the 222 mod 11 is 5. Hopefully this makes sense. I mean, this is a very, very elementary application of this theorem. It's just one little baby application of this, okay? But you see the principle behind it is that you can reduce the computation of a very big power. You don't really need to compute it. You can just, I did this by hand, right? There was nothing fancy about this computation, right? Okay. So hopefully this makes sense. So let's move on to, and we'll see an application of Fermat's little theorem when we do RSA. Okay, so today I'm going to finish for 4.4. I have maybe 5-10 minutes left. And then I'm going to do some slides, which is an introduction to cryptography. I'm not going to start RSA per se today. Okay, I will do that, I would guess, tomorrow. Okay. Okay, so primitive roots. I still have mixed feelings about talking about primitive roots. It's a fundamental concept, or we're not really going to use it in any sort of way. So it's sort of, yeah, but what the hell? It's natural, it's important, but we're not going to do way more than just seeing the definition. That's it. Okay. So what is this? Okay, so here's sort of an idea or motivation. And this is where I'm having a little trouble here because we're not going to go very far with this. So it's difficult for me to motivate this in any sort of. I'll try, but after I've given you the actual definition and computations. Okay, but so look at Zn. Okay, so Zn, it has an additive generator. So does Z actually. What do I mean by that? It means that there is a number that in Zn that if I add it to itself, repeatedly, I will generate the whole set, right? So 1, 1 plus 1, 1 plus 1 plus 1, and so on. You will get this way, you will obtain all the elements of Zn. Hopefully that's clear, okay? So if I add 1 to itself sufficiently many times, I will go 1, 2, 3, 4, 5, right up to n, which is back to 0, so I'll get everybody, okay? Okay, that's not very interesting, but what about the following question? So question, does it have a multiplicative generator? So is it possible to find a number such that if I take, so rather than add this number to itself, you multiply this number by itself sufficiently many times, right? So you're taking powers of this number. Okay, so let's say it's r. So it means that r squared, r cubed, and so on. Can you obtain all the elements in Zn? Okay, so the answer is no. So not a very interesting question, maybe. So, but we can tweak the question. Okay, and so the answer is no. We can't expect, in general, to get 0 in any nice way. So it's possible, but that's 0 is sort of annoying here. So I'm going to tweak the question. Okay, so let's change the question. So can you find r such that r squared, r cubed, and keep on going like that, and you will this way obtain all non-zero elements of Zn. Okay, so the answer is not always, but there is a case where the answer is yes, and that's when n is prime, and that's what I want to look at. Okay, so answer yes if n is prime. Okay, so let me define this. Okay, so that's what we call a primitive root. So a primitive root is a multiplicative generator for Zp, p prime. Okay, so multiplicative generator means you generate all the non-zero numbers. Okay, so here's my definition. So let p be a prime. So a primitive, no, sorry, let's give it a name. So R in Zp is a primitive root mod p if every non-zero element of Zp is of the form r to the k. Let's write e here. E for exponent, mod p. Okay, so you can either view it as multiplying in Zp, or if you're multiplying in Z, then you reduce mod p, either way, okay? So you have this number and you take these powers and you'll be able to generate all the non-zero representatives mod p from 1 to p minus 1, okay? So let's look at some examples and non-examples to illustrate, okay? So here's an example of what this is about. Okay, let's take, and this will also illustrate this good old thing I've been repeating ad nauseam about trying to get the numbers small when you're doing computations. Okay, so let's find a primitive root mod 11. 2 is a pretty good candidate when you're looking for primitive roots. Okay, it's small and it often works, not always. I'll get back to that in just a sec. So 2 is a primitive root. Primitive root mod 11. Here's the proof. So how do you prove that? Well, you check. You just take the powers of 2 and you check that you get everything you need. Okay. Okay, so let's see. So 2 power 1 is 2. 2 power 2 is 4. 2 power 3 is 8. Again, I'm looking at all this mod 11, right? 2 power 4 is 16. Mod 11 is 5, right? Okay, so far so good. 2 power 5. Now, it is 32. 2 power 5 is 32, but I don't need to go there. So let me put this here. So notice that in Z11, 2 power 5, power in Z11 is 2 power 4 times 2, right? But I've already reduced 2 power 4, and I know it's 5. So this is the same as 5 times 2, which is 10, right? So you see that I don't need to go 2 power 5. I don't need to do it. So this is 10, okay? Which happens to be the same as -1. I really like the -1 trick. That's pretty cool, okay? So notice also that 10 is the same as -1 mod 11. So 2 power 6 is 2 times -1, which is -2 mod 11. That's 9, right? So I'm not going to put comments on all of them. I'll let you figure it out by yourselves after, but so that you're not totally lost when you read this again. So then 2 power 6 is 2 times -1 mod 11, which is the same as 9, right? I can always work on the clock with 11 hours, right? Okay, so I keep on going. 2 power 7. Well, numbers now are small, so it's fine. So 18 mod 11 is 7. Then 2 power 8, that's 2 times 7, which is 14, which is 3. 2 power 9, that's 2 times 3, this is 6. 2 power 10, what do we expect? So if you're doing a computation like this and you get to that, this is the last one. Why? Because of Fermat's little theorem, right? So notice Fermat's little theorem tells you this must be 1, right? Because it's 2 to the power p minus 1. Okay, and of course 11 doesn't divide 2. I chose the number inside Z11, so 11 doesn't divide it. So this, and it works, right? 2 times 6 is 12, which is 1. Did I get every number? Yes. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We got them all. Yes. Okay. Now, you might be thinking, well, why doesn't it always work? And this is this is tricky. This is why I have mixed feelings about presenting this, because it's really interesting, but if we don't spend any time with it, it's sort of very mysterious, and you have to spend a lot of time with it to see a little bit the patterns, and it takes just more advanced stuff to do this, to see this. But at least you see, I mean, it's a simple concept. I mean, as long as you know reduction mod p, then it's a simple definition. You have a number and you take all its powers, and you can generate all the numbers between 1 and p minus 1 this way. Now, a question you might have is you say, how long do I have to go to make sure that I'm going to hit them all? And that would be a very good question. If that question went into your head, that's excellent thinking, okay? The answer is a good answer. The answer is you don't have to go very far. Actually, if you're going to get them, you are going to get them in the first p minus 1 steps. Okay, so this is an observation. This is not obvious, okay, but this is a fact. Okay, so let me add this remark. So how far do we need to go to verify that a given R is a primitive root? Answer, and again, this is not obvious. I mean, it's not obvious. It's not obvious at this point. I could show you stuff that would make it obvious, but you're not supposed to be listening to me at this point, looking at this and saying, yeah, oh yeah, I see why. Okay, if that's no. Answer, if R is a primitive root, then R power 1, R power 2, right up to R to the p minus 1 will be precisely what you're looking for. You'll get them all. Okay, so this will be equal to Zn star. Zn star is Zn except 0. Okay, so this is good news, right? Because I mean, in just looking at the definition, you might have to go up to millions for the powers to eventually get what you want. You don't need to do that. You will get them all once you've reached the p minus 1th power. Okay, so if you don't have them all by that point, you'll never get them all. So let me show you an example, a non-example, so you'll see what this means. Okay, so let's take a look. So 3 is not a primitive root mod.
Sir,
Yep.
can you go up just a little? I haven't
Sure.
had time to
Yeah,
write the answer
sure.
down.
I'll have some coffee. Okay, so hopefully you see what I'm saying here is that, so let's say I give you a number R and a mod and a prime P, and I ask you, is it a primitive root mod P? Then you start looking at these powers. In principle, you might have to go up to very, very high powers. There's nothing in the definition that tells you that you're going to get them all very soon. But the fact is, this is true. It is true that you all you need to do is check those. And I'm not going to try to convince you of this. It'll just take us off into another direction. But let me show you a good example. Are you okay now? Yeah, I can move up, I guess. Okay, so let me show you that 3 is not a primitive root mod 11, and we'll see very soon why. Okay, so let's check. So 3 power 1 is 3. Again, I'm working mod 11 here everywhere. 3 power 2 is 9, which is minus 2, by the way. So 3 times minus 2 is minus 6, which is 5. You see, I didn't even need to compute 3 cubed. I don't want to go there. Then 3 power 4, and that's 3 times 5, 15 mod 11, that's 4. And then 3 power 5, that'll be 3 times 4, which is 12. And I hit 1. So why do I immediately know that this is not a primitive root mod 11? Well, I got 3, 9, 5, 4, 1. What's going to happen from this point on? Hopefully you see. Yes. So then when you multiply by 3, you're going to go back to the 3 and then 9, and you're just going to loop. That's exactly. So from this point on, from this point, we will loop. Okay, so you can even at this point, I know 100% sure that 3 is not a primitive root. I've hit 1 too soon. Okay, in fact, if you don't hit 1 at that point, you know you have a primitive root, but that's not obvious. But that's the point. Okay, so now a natural question would be, how do I know? Okay, so let's state a theorem which is highly not obvious. Theorem: for every prime p, there exists a primitive root mod p. Okay, this is not obvious. I was trying to see what the simplest proof of this is. The simplest proof that I know is pretty complicated. So, but it's a fact. So it's a fact that there, for every prime p, there is a number that will generate by powers all the numbers from 1 to p minus 1. Now, this is a non-constructive proof, okay? And it's a non-constructive proof. There are many questions about, in the sense that finding, if I give you a prime p and I ask you, find a primitive root for that prime p, there's no like simple formula that will give you a primitive root. Okay, so there is no known simple way to produce a primitive root. For example, I think it's still open whether, I'm not sure about this, but for example, here question, is 2 a primitive root for infinitely many primes p? I think this is still not known. It might have been resolved in a lot, but when I was in university as a student, it was not known. Yeah. Okay. Now, this is related to a public key cryptography system, which we're not going to see, which is called El Gamal. So let me just put that as a comment here, a little aside. So the El Gamal crypto system is based on what we call the discrete logarithm. Discrete logarithm. So here's the idea. We're not going to see El Gamal. We're going to see RSA. It's a different. I mean, they're similar flavor. We're going to see RSA, not El Gamal. So what's the discrete logarithm? So you fix a prime p, and you have to find one. You have to compute some primitive root. Fix a primitive root R mod p. Okay, so think, for example, for p equals 11, we had 2 as our primitive root. Okay, so what does it mean? It means that every number is congruent to r to some power mod p. Okay, so every element of 1, 2, right up to p minus 1 is congruent to r exponent e mod p for some exponent e, right? So let me just scroll back up to 11 here, okay? So you see 6 is 2 power 9. So the exponent you need is 9. That's for when you fix the base 2. For 9, you have exponent 6. For 10, it's exponent 5. For 8, exponent 3. Looks pretty chaotic. And in fact, we think it is, in a sense, very, very chaotic. So here's, I'm going back to this. Okay, so this is called, E is called the discrete logarithm of, oops, I didn't give a name to my element. Every element, let's say A, of A mod P. There's a lot of stuff, but I'm just mentioning this just in passing. We're not going to go back to that, okay? So base R, okay? So for every number between 1 and P minus 1, there is an exponent I can give to that primitive root that will give me my number. That's what we call the discrete logarithm. It is believed. So it is easy computationally to compute. Yes, it's redundant. Sorry, no style. To compute R to the power, whatever power, any power, powers of R. Even if they get big, if you're mod P, you can compute these big powers efficiently. It can be done efficiently, okay? But the opposite, so taking powers is easy. Finding the power is thought to be hard computationally. So it is thought to be difficult computationally to find the discrete logarithm. Okay, so in other words, what this is what we call it's believed to be a one-way function. Okay, so in one direction, it's easy to compute, and in the reverse direction, it would be very difficult to compute computationally. Okay, I'll get back to this concept in just a minute in more general terms, but this is the basis for the Al-Gamal system to encode. So for encoding, so that's the idea. Okay, but so you see where the primitive root gets into play here. Okay, but again, this is just for your general culture. Okay, so we're not, this is not going to be on any quiz test or anything like that. Okay, any questions, comments? So this is the end of 4.4, which is the end of the theoretical part in some sense of chapter 4. Okay, so we're going to move to chapter 4.6. Hello. Let's share. Do we know when the next test will be, sir? Yes, the next test should be, I was thinking April, is it 6th? Is that what I?
Yeah, you sent April 6th.
Yeah. So that or it could be the week before, but if you are against that, but I think, no, I think, no, April 6th is good. I think that would be good. Yeah. Can you guys see the slides? Yes?
Yeah.
All right. Okay. So I'm good with that. Yeah. Okay. So this is just like a high-level introduction to cryptography and to RSA per se, RSA for real, I will do this week, but not today. Okay, so this is just an intro. Okay, all right. So what I'm doing today is the overview that I'm talking about on this slide here. Okay. Okay, so some basic definitions. Alice and Bob would like to exchange information in a secure fashion. So they want to exchange, to send each other information. And if anybody is eavesdropping, they wouldn't be able to know what Alice and Bob are talking about. Okay. Eve is the attacker, is the opponent of Alice and Bob in this game. Eve for eavesdropper. So she can see what's going on between Alice and Bob, and she's trying to understand what Alice and Bob are trying to say. So what we call the plain text, this is the message. So usually Alice is the sender, but this could change. But anyway, so Alice is sending a message to Bob. This would be the plain text. That's what would have meaning for Bob. The ciphertext, this is the encoded version of the plain text. Okay, so Alice will obviously, if she wants to send the information to Bob in a secure way, she has to encode her message using what we call a cipher or an encryption protocol. Okay, so this is a method, whatever it is, okay, in which Alice is going to transform the plain text into a ciphertext. And now she can send this to Bob. And even if Eve sees the ciphertext, she hopefully will not be able to figure out the plain text from the ciphertext. Obviously, Alice and Bob have to agree in advance, because otherwise Bob will not be able to read either what's going on. Bob has to know how Alice encoded her plain text, right? Cryptanalysis is the name that is given to what Eve does. Okay, so she's trying to break the code. She's trying to recover the plain text from the ciphertext without any, or I mean, we'll get to that because there is some knowledge, but in a sense, without the key knowledge of the encryption method. Okay, so that's, yes. Okay, now we're going to go back to chapter 2 briefly. I just recall what a bijection is, what we also call the one-to-one correspondence. This is a function which is one-to-one and onto. So it means that if you give it two different inputs, it will give you two different outputs. It's not going to crush two inputs to the same output. Okay. And it is onto, so everything in the codomain will be hit. Okay. Another way of defining a bijection, we defined it also as follows. Its equivalent is that it has an inverse. So there's an inverse function going from the codomain of f to the domain of f, goes the other direction, which undoes what f did, right? So if little a was sent to little b, then little b will be sent back to little a. And the existence of an inverse is, the conditions are precisely that the function is one-to-one. Otherwise, you don't know where to go. And it has to be onto, because you want the inverse to be defined everywhere. Okay. So if I have a function f that encodes plain text, okay, I want it to be a bijection, because I don't want to encode two different things that they become the same thing. That would be bad, right? So the set of possible ciphertext, so the function f maps all the plain text to all the ciphertext. It has to be a bijection. So the inverse is the decoding function. Okay, so if f encodes, f inverse decodes. Okay, so this is very, very general, right? We're not telling you what f is. But let's see some actual examples. This is one of the earliest, if not the earliest known encoding method, which is called the Caesar cipher. We're going to use plain text in English, but we're going to, for ease of discussion, we're going to see the letters as elements of Z26. So so we have the letters, Latin letters, A, B, C, D, right up to Z. There are 26 of them. So I'm gonna simply give them numbers. That's not the encoding, right? That wouldn't be very, very secret. So A is 0, B is 1, C is 2, right up to 25, okay? So here's a very simple function. So it's a function from Z26 to Z26, and it is defined by f of p is p plus 3. Now, I could have written this as p plus the little plus 26, so it's the plus in Z26, or as p plus 3 mod 26. But what it does, if you look at Z26 as a clock, it just shifts by 3, right? Plus 3, that's what it does, okay? So that's a very simple function. Hopefully you see that this is a bijection, right? So no two values will be sent to the same thing. Obviously they're shifted, right? And you're going to hit everything for sure. So it's a bijection, so it should have an inverse, and you can probably guess the inverse just looking at it, right? If you're shifting by 3 clockwise, then the inverse will be shifting by 3 anti-clockwise, right? That should be clear. But in any case, we'll get back to the inverse. But how do we use that as a cipher? Well, that's very simple. Okay, so if you look at some plain text like the one which is here, meet in the park, we have two spies, and one of them wants to meet the other one in the park. So the spy Alice wants to send the plain text meet in the park. So in numbers, I just wrote down the numbers that correspond. So this is just the simple numbering of the letters as we discussed on the previous slide. And then I apply F. So I add 3 to each one of these values. Unfortunately, I wanted to change my example, but anyway, I wanted to have a letter which is closer to 26 so that it would actually loop back, but it doesn't make any difference. So you add 3 mod 26 to each of these numbers, and then you just revert back to letters to see how jumbled up this is, right? So the ciphertext, so if you're Eve, what you would, if you're intercepting this message, this is what you see, PHHWLQWKHSDUN. It's just junk, right? It's just, so that's kind of cute, right? So this is the ciphertext. That's what Eve sees, okay? Now, Bob is going to receive this also, right? So what does Bob do? Bob will apply the inverse function. As I said, if the cipher is +3, then the inverse of F is just -3, right? You just flip back. So now I have a different ciphertext because it's a bit more interesting. So the ciphertext that Bob receives is VXU SULVH. So Bob writes down the numbers corresponding to these letters, then subtracts 3 from each one of them, and then translates that to letters. And it is a wonderful message, surprise. So yes, so this here is just the essence of encryption right there. Okay, so it's a very simple function, but you see how this works. Okay, all right. Now, here's a slight little generalization of this cipher. So of course we shifted by 3, but we could have shifted by any other value except 0. 0 is not very good, but you can shift by any number, right? But you can make it even more complicated by using a function of the form AP plus K mod 26. Okay, so before you shift by K, you multiply the input. P is not a prime here, by the way. Yeah, obviously. You multiply by A, some A that you choose in advance, right? The only thing is that you need this to be a bijection. So how do you make sure that this is a bijection? We'll see that in just a sec. here's an example. If you take the function 7p plus 3 mod 26, okay, in this case, the letter k, which is 10, will become v. 73 mod 26 is 21. That corresponds to the letter v. Okay, so this will jumble up the letters in a slightly different way than just shifting. Okay. So how do you make sure this is a bijection? You want to make sure that A doesn't crush two things to the same thing. How do you make sure? Just pick A such that the GCD of A and 26 is 1. This might ring a bell. Oh yeah, by the way, yes, this is something I wanted to say. I uploaded some slides that review briefly all the stuff from 4.1 to 4.3. So it doesn't have the Chinese remainder theorem, and it doesn't have Fermat's little theorem, but otherwise it has all the basics. I did this last year because COVID hit, and so school was stopped for a few weeks. So I knew that coming back, the students would have maybe forgotten a lot of stuff. So I produced those slides, but I thought you could also use them as well. So they are there. Okay, so if you choose A to be relatively prime to 26, then you know it has an inverse mod 26. Let's call that A bar. Okay, so A times A bar is 1 mod 26. Okay, so I'd like now to decrypt what's being sent to me. So if I know that the encoding function is AP plus K, this is what I get. I receive C, which is A times P plus K mod 26. I need to find P. That's what I want. Okay. So first of all, AP, right? C is the same as AP plus K, congruent mod 26. So AP is congruent to C minus K mod 26. Obviously, I'm going to subtract K to start with. And then I want to get rid of this A, so I'm going to multiply by its inverse, mod 26. So I multiply both sides by A bar. So I know that P will be A bar times C minus K mod 26. So that's my decoding function. So when I get C, I subtract K, multiply by A bar, and I get the original value. Okay, so and then I compute an example here. But you see the idea. So if you encode by a function of the form, and this is called an affine cipher, AP plus K, where A is invertible mod 26, then it's easy to get back what you want. Okay. All right. Now, the problem with affine ciphers is that they're not very good. So their main obvious weakness is they are vulnerable to what's called statistical analysis. Okay, so in English, if you take a long enough book or text, random text book, if you count the number of E's in it, you will see that there are more of them than any other letter. Okay, and so the frequency is about 13% of E's in the text and 8% of A's and O's, then I and N. And you see that some letters are more frequent than others. So if Eve is intercepting a ciphertext, which is pretty long, and she sees that the most common letter is X, okay, she might make a guess that it's actually encoding E. Now, if you know that it's an affine cipher, now you've got much less things to consider. Knowing that f of e is equal to x, you can try now to see what the possible values for a and k might be, right? And you try. And so you see if you get still junk when you're trying with those values. If not, then you know you've got the right encoding function, okay? So so from this point of view, an affine cipher is not very good. It's easy to break. Okay, so what you can do is use a completely different approach, is the notion of block cipher. Okay, so let's take a look at what a block cipher is. Very simple. It's actually simpler than affine. Okay, And so let's take a look at the simplest block cipher, which is the transposition cipher. Okay, so what is a permutation? I don't know if I had defined this before, but a permutation is a bijection from a set to itself. Okay, that's the name we give to a bijection from a set to itself. It's called a permutation. Okay, so here I'll have a permutation sigma, and that I fix. Okay, and my encryption method will be the following. Okay, so sigma is a permutation on the set 1 to m for some fixed m. Okay, I'm going to take my plain text and I'm going to cut it up into blocks of length m. If at the end I'm missing letters, I'll just add junk. Okay, it makes no difference. I'm just going to add junk to pad until I get a multiple of m. Okay, and now I take a block of length m, p1, p2 to pm. These are letters in my block, and I jumble them up following this permutation. So p1, p2, pm will be rewritten as p sigma 1, p sigma 2, right up to p sigma n. So basically, I'm mixing the letters, and I'm going to send that. Okay. Now, what do you do to decrypt? As long as you know how the mix has been done, you can demix it by just applying the inverse permutation. So let me show you, especially since in the book, there's an example which is totally wrong. So let me show you the right way to do this. Okay. So in the book in 4.6, example 6, you can just like in the famous movie, you just rip the page out. So here's the correct method to do this. Okay, so I'm choosing m to be 4. So my blocks will have length 4. And my permutation, I just chose some permutation. Sigma of 1 is 3, sigma of 2 is 1, sigma of 3 is 4, sigma of 4 is 2. So you see it's a bijection from the set 1, 2, 3, 4 to the set 1, 2, 3, 4. Okay, so how does this go? The block P1, P2, P3, P4 will be encoded as P sigma 1, P sigma 2, P sigma 3, P sigma 4. I just write down what these are. Sigma 1 is 3, so that's P3. Sigma 2 is 1, so that's P1. Sigma 3 is 4, that's P4. And sigma 4 is 2, is P2. Okay, so here's how this goes. You have your plain text, which is pirate attack. You split that up into blocks of length 4. So 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. And then this is the ciphertext. So notice here, okay, the first letter here should be P3. So I look up the third letter here, it is R, so that's R. The second one should be P1, that's the first letter, goes here. In the book, they use the inverse permutation. It's wrong. That's not the right way. Okay. A here, what is that? Sorry. So the third one should be P4. So that's the fourth one, which is A. And finally, the last one, which is I. Okay. And you do the same for each block. Okay. So that's the ciphertext. Now you'll agree with me that this doesn't look like a very, very powerful cipher, right? It's not. Okay, for other reasons than the statistical analysis, right? But we'll get back to that in a sec. Okay, so now this is the ciphertext. Okay, here now, so how do you decode? Okay, so our sigma of 1 is 3, sigma of 2 is 1, sigma of 3 is 4, sigma of 4 is 2. What is the inverse? Well, sigma inverse of 1 will be 2, sigma inverse of 2 is 4, sigma inverse of 3 is 1, and sigma inverse of 4 is 3. So it just goes in the other direction. This is sigma inverse. Okay, so now how do you decrypt? You receive a block, C1, C2, C3, C4. You rewrite it following sigma inverse. Be careful. This gets confusing if you don't follow the recipe. I mean, we understand at a high level how this goes, right? But if you start writing out things, you have to be careful. Okay. So now sigma inverse is the one that I use. So this is sigma inverse of 1, which is 2. Sigma inverse of 2 is 4, and so on. Okay, so if I receive this as my ciphertext, I split it up into blocks of length 4. Here we go. And then I apply my recipe, right? So for the first symbol here, I want to see the second one, C2, right? So this is C2, it'll be U, then it'll be C4 is S, then C1 is E, so U, S, E, W. Let's see what we get. Yes, U, S, E, W. Then the same thing for the next block, then the same thing for the next block. And so the plain text, oops, sorry, is use water hose. I don't know, I took this from the book. I think, maybe not. I guess so. I guess I did. Okay, so that's the plain text. Okay, so the encryption and decryption methods are exactly the same. One is using sigma, the other one is using sigma inverse. So how do you decode what you receive is C1, C2, C3, C4, and then you write down C2, C4, C1, C3. Okay, so you look up each one of the letters in the block. Does that make sense? Does that make sense? I don't. Does that make sense? You have to sort of.
Yes, it does.
Yeah, good. So you have to sort of take a piece of paper and do a few examples by yourself, right? It's not very deep. It's not just, you have to just, you know. Okay. All right. Okay. Yes. Opening the door. Okay, so one thing we can do is to make a stronger cipher is to combine, right? If an affine cipher with a block cipher, that would be even better than either of those two. But it is still not so secure. There are known methods to attack these ciphers. Okay, so if Eve is a good mathematician, she'll be able to figure out what's going on. So one question I mean, so there's the question of how do you create stronger and stronger encryption? Sorry about that. So how do you create stronger and stronger encryption? That is one question, which leads to the question, is there an optimal encryption method? Is there a totally unbreakable encryption method? And the answer is yes, there is such a thing. It's called the one-time pad, and it's pretty simple. So let me show you what the one-time pad is, and it is used. It is okay. So this goes back to the 20s, and until recently, I mean, I guess maybe it's still used. There's this hotline between the American and Russian presidents, and it is encrypted with the one-time pad, and it is basically unbreakable. It's unbreakable. It's unbreakable.
Député.
Yeah. Hello. Yes. Okay. Oh, just give me a sec. Sorry. Sorry about that. Okay, so here's how this thing works. Okay, so the plain text is a sequence of bits. Okay, and let's call it P. And an encryption key, which we'll call K, is a bunch of bits which has exactly the same length as P. Okay, this is agreed upon in advance by Alice and Bob, And how do they produce this thing? They flip a coin p times. Okay, so it is a random sequence of bits. Okay, so the plain text is this bunch of bits p, okay, and the key is a bunch of bits k. They have the same length. What is the ciphertext? You take the XOR of p and k. So again, remember what the XOR is. So you take this bitwise. Okay, so if it's 0 plus 0, you get 0. If it's 1 plus 1, you get 1. And if it's 0 plus 1 or 1 plus 0, you get 1. Okay, so there's an example right here. So if P is 1, 1, 0, 1, 0, and K is 0, 1, 0, 1, 1, then the encrypted version, the ciphertext 1, 1, 0, 1, 0, XOR 0, 1, 0, 1, 1, this will be 1, 0, yes, 0, yes. I'm just computing it. 1 plus 1 is 0, and then 0 plus 1 is 1. Yes, so that's the encrypted version. Okay, so it's very simple. Very, very simple, right? I lost, damn. Sorry. Ah, there you are. Okay. So how do you decrypt? First of all, let's see that. That's really silly. You just XOR again, right? So it turns out that XOR of a bit with itself, right, is always 0. 0 plus 0 is 0, and 1 plus 1 is 0, right? So if you do C plus K, right, this will be P plus K plus K. So the K plus K just disappears. It'll be 0. So you get back P, okay? So encryption and decryption are really silly. It's just really super simple, okay? Now, why is this unbreakable? And this is, I mean, you should really think about this. This is very interesting. Okay, so what does Eve see? Okay, she sees a bunch of bits, which is P plus K. Okay, now K is a random sequence of bits. This was produced by flipping a coin. Okay, which means that P plus K is itself a random sequence of bits. Why is that? So think of what does the XOR do? Okay, so you have a bit in P, and you XOR with a random bit. So I called it Ki. Okay, the ith bit of K. Okay, so what happens is you either flip the value of Pi or not, depending on a coin flip, right? So that's basically what we're doing. In a sense, we're doing, so we have a message and we flip a coin. Okay, for each single bit, we flip a coin, and if it comes up heads, we don't change that bit, and if it comes up tails, we change the bit. So it's basically, it's a totally random procedure on the original sequence of bits. Okay, so there is no way for Eve to figure out how these, I mean, unless you know how the bits were flipped, there is no way, it's just totally random. Okay, so we're adding random noise to the message. Okay. So, all right, so why don't we always use that? If it's perfect, if it's unbreakable, you can maybe see one obvious big problem with this one-time pad. It's the length of the key, right? That's really, really, really bad. So you need an encryption key, which is as long as the message. Okay, so you have to produce a random sequence of bits, which is as long as the message. And then, I mean, if Bob receives this message encrypted, right? If Bob needs to know what the encryption key is, so Alice and Bob have to actually exchange this key. And this is a completely separate problem that we'll get into in just a sec. So they have to exchange this key because, I mean, that's the only way to decrypt, right? And the last thing, this is interesting, is a bit more technical, but it's called a one-time pad because you're not supposed to reuse it. So if you use this key, you should throw it away immediately after you've used it, because if you start using it more times, then Eve will get some information out of this. I did a little computation here, it's not very convincing, but apparently in the 50s, the NSA actually managed to break some codes from the Soviets because they were getting lazy and reusing the same keys over and over again. And so apparently, I don't know the details of this, but so this one-time pad, the key has to be used exactly once and thrown away. Okay, so basically you're flipping a coin for every single time you're doing this, every single letter in your message. Okay. Yeah. Okay. But it's interesting that there is such a thing as an unbreakable code in theory. Okay. And it's used. If you don't have to exchange a lot of information often, then you're fine. Okay. So, which brings us to public key cryptography, which is what we're interested in. Everything we've talked about up to this point are private key crypto systems, which means what? It means that the encryption method, if you know it, it'll allow you to decrypt, right? Every example that I've given you here, if you know how the thing was encrypted, then you know how to decrypt. That's it, okay? Which means that there has to be an exchange of information between Alice and Bob, right? So if Alice is encoding in a certain way, Bob has to know how. Now, if Alice picks up the phone and calls Bob and says, oh, look, I'm going to be using this and this, blah, 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 then of course Eve can intercept that. And so all of this is for nothing, right? So the key has to be exchanged in a secret way. Now, how do you, I mean, it seems like it's circular, right? If you have to exchange the key, you have to do this in a secure fashion. How was it done in the old days? You'd have people walking around with suitcases locked and minute. Damn. Yeah, handcuffs. They were handcuffed to, and they would just actually bring the keys to the bank and they would open it. Okay, that's the key we're going to use, and that's it. So the keys had to be actually delivered physically, right? As it is in the one-time pad. In the one-time pad, I mean, you actually have to physically give the embassy the key, right? There's no other way, okay? So this is really, that's fine if there are only two people talking, but let's say that the bank, as you know where this is going, the bank wants to have secure information delivered to all its clients, right? Well, it's not, it can't deliver a key to each single client individually. That doesn't work, okay? So people started thinking about this and eventually came up with the concept of public key crypto system, which is a totally non-intuitive thing, which is that in a public key crypto system, the encryption key is public, but it's not sufficient to decrypt. Now, this is super not obvious how you do this. I mean, people who actually figured this out were really smart, but the whole point is the notion of a one-way function. Okay, all the known systems right up to this point are based on number theory, arithmetic, just like that's why we developed everything that we did up to this point. Okay, but the general idea is the notion of one-way function. Okay, so what's a one-way function? Is a function, as I said when I was talking about El Gamal, it's in one direction, the function is easy to compute computationally, so you can do it fast and efficiently. But once you have the output, it's difficult to compute the input, okay? So I talked about this discrete logarithm, that's a potential one-way function, okay? So the other one that we talked about, and this is the one that's going to be, that will be, I'm almost done. Sorry, I'm tired. Underlying RSA is multiplying and factoring. Okay, so that would be the potential one-way function behind RSA. So we know how to multiply numbers efficiently. So we're going to take two very, very big primes, multiply them together. Okay, and that we can do easily. but factoring that is thought to be hard. Still, we don't know that it is actually hard, okay? But in principle, it is difficult, okay? So this is the trick behind RSA, and we'll see that in a lot of detail, in all its gory details next time. I think that's my last slide. Maybe not. Yeah. Okay, so this is my last slide. If you're interested in these things, I can recommend two very, very cool books. And they are, I mean, yeah, you have access to the college. The code book is at the library at the college. This is a really cool book. History of encryption, written by very smart, interesting fellow by the name of Simon Singh. And the other one, if you don't know this book, it's a bit advanced for you guys, but it's like, it's such a cool book. Quantum Computing Since Democritus, just the title is worth it. Chapter 8 talks about encryption. Scott Aronson is a wonderful writer. This is very funny. So if you want more on this, you can go and take a look at these books. And yes, questions, comments, anything. Because I'm done for today.